Okay, so we're looking at equilibrium here for objects that have dimension. So we've got some different equations we can use now. Now we did particle equilibrium already, where we looked at just force equations. We're going to add another equation here that the moments about anywhere you care to take moments about is zero. Because if the moments are not zero, the object would start to spin. So in equilibrium here, what we're looking at is F equals ma. We're looking at an acceleration of zero. So the sum of forces is zero, as is the sum of moments. Okay. All right, now with 2D analysis, we'll have three independent equations. You can find three unknowns with this. So we got sum of fx is zero, sum of fy is zero, and the sum of moments about anywhere you want to take it is zero. Now, you could generate as many moment equations as you want, but they're not independent of one another. You can replace these force equations with moment equations, so you could conceivably take three moments rather than two force and one moment. You could take one force and two moments. But once you get beyond three equations in 2D equilibrium, you get into redundant equations, okay? So keep that in mind. So generally the simplest way to go is sum of fx is zero, sum of fy is zero, sum of moments is zero. Now, if you're in 3D, you got three force equations plus three moment equations. So that's six equations. You can find six unknowns. If you got more unknowns than you've got equations to find, that's called statically indeterminate. And you'll start to learn about that in strength of materials, not in this class. Okay, so what we're going to do, we're going to use these equations to solve for the reactions. Okay, so we have applied forces that we assume, and those are things like lifting loads or snow loads or wind loads or whatever the heck it is, weights and stuff like that. And you assume those, and those act on your support, whatever that happens to be, a beam or a column or whatever it is. Then at the supports, you've got reactions. So you use these statics equations to find the reactions at the supports. And then once you've got the actions and the reactions, you know all the forces acting on the object, and you can design it then. But before you can design it, you got to know all the forces. And that includes both what you're applying to it plus how the reactions hold it up. Okay? So this is the first step in doing design. And you need to know this, what these reactions are before you can design something to withstand all the loads. So that's what we're up to here. This is probably the most important concept in the class. It's just this idea of equilibrium. Now, another thing I want to mention on this is that signs have meaning here. The signs you put into an equation signify the direction you're assuming things act. Okay? The signs of your answers that you get out of the equation, they tell you whether your assumptions of direction were correct or not. Okay? So the signs mean different things depending on whether you're putting stuff into an equation or looking at your answers. So you want to kind of keep that straight too. Okay? So what we're going to do, we're going to assume what the applied forces are, and those will be given to you in this class. In the working world, you'll have to figure them out, but in this class, they're given. Then we'll look at a free body diagram, draw the reactions on there, and then use the statics equations to solve for them. Once you've got everything, then you can design the beam or whatever it is you're working on. Okay. And then we have this bit here about signs. So let's just have a quick look at signs here. Let's say we want to find this reaction at A. I would model it. I would see it, that's a pin joint. So I've got an upward reaction there. I'm ignoring RAX, it looks like. It's on there, but I'm ignoring it. Okay. So let's say I want to find RA. I'm assuming it's up over here. So being as it's up, if I take a moment about the other support, which is B, what I'm going to have is 2 meters, and 2 meters makes 4 meters times RA for a moment about B. That's a clockwise moment, so that's a negative for RA. That's what goes into the equation. Because I'm taking moments about B in this example, and I assume that RA acts up, which leads to a clockwise moment, which is negative. Okay? Now, when I worked through this, I got a positive answer. That meant that RA is as I assumed, it's up. Okay? So that positive answer meant that, yes, I assumed correctly RA is up. Okay? Now, if you assume that RA was down, which you could assume, if it's down, when I take the moments about B, now I've got RA going counterclockwise. Okay? So that goes into the moment equation as a positive now, if I assume RA is down. Because a counterclockwise moment about B is positive. When I solve for RA, though, I'll get a negative answer. And what that means is my assumption was not correct. It doesn't act down, it acts up. Okay? So notice that regardless of which direction I assumed RA to act, looking at the numbers and the signs on the answers, in both cases, I get that RA is upward. Okay? So you just have to be aware what those signs mean. When you put them into the equations, it's the direction that the things act. When you look at what comes out of the equations on the answer, it's whether your assumption was correct or not. All right.
Can you just flip the sign at the end?
Yes. Yeah, to fix it, it's quite simple. You just point it the other direction. That's all you got to do. If you get a negative answer. So it's not like you got to rerun or anything, redo an equation or anything like that. Just turn it around. That's all you got to do.
RA is a force, right?
Yes. Is that a reaction? R means reaction. It's the force at A.
Okay.
Okay. And we'll come back to this, but I just thought I'd mention that this thing on signs can be a little confusing to people, so I just wanted to point that out. The signs mean different things depending on which side of that equation you're using them, okay? Whether you're putting them in and their direction, or whether you're taking them out of the equation, which either verifies or tells you that your assumption was wrong, one or the other. Okay. Okay, so we're going to work on equilibrium here for a while. We're going to start with simple beams and columns like you see there. There's the walkway coming from the north parking lot. So we got beams. Beams run horizontally and support loads. That's a beam. Columns run vertically and support loads. Okay, so there's a beam and a column. And they're simple because they're just, nothing really fancy going on with those things. They're just straight, either horizontal or vertical structural members, as you'd call them. And we run into these in a lot of different places in structural. The civil world is full of examples of these things, okay? You can consider that to be a column, that power pole. Just a vertical member, nice and straight and simple there. There's Takina Hall. You can see those T-beams running into that inverted T. You got all this stuff going on. So these are beams. They're held up by a main beam there, and that's held up by an even bigger beam going that way, and then we got a column right there, okay? So it's simple beams and columns. There's a bridge. See the supports on either end. Got that bridge running like a beam across. Column here in the middle holding it up. There's a truck. If you design that truck, or if I did, I'd think of that as being a beam running across like that, okay? So this comes up all the time. So let's have a look at 400 and let's work through one of these. Let's say we've got what we call an overhanging beam here. So we've got a pin joint at A, we got a roller at C, we've got these loads, and notice the beam extends over the roller at C, so that's called an overhang, is what that's referred to. Let's first, and let's always get in the habit of doing this, take that sketch and make it into a free body diagram. Now, that isn't that big of a task. Look at the supports. and instead of having supports there, put a force in for the supports. Remember, the forces of the supports show what motion is prevented. It takes a force to prevent a motion. So look at what motion C prevents and put in a force to mimic that. Look at the motions that A prevents and look at and put in forces for those, okay? And I would suggest just using the sketch itself, because it's just quicker and more direct and it's all dimensioned and good to go. Okay, so you probably just need a couple arrows in there. Maybe 3 arrows actually. So let's step it first. Okay. Helps to draw a boundary around it sometimes. So we all on the same page there? We got REX, REY, and RC. We use R for reactions. That's typically the letter that we use to indicate reactions, although it really doesn't matter. I've seen R, I've seen F sometimes. I just use R out of habit. Okay, so we got a pin joint and we got a roller. So the roller prevents motion up and down, so I got a vertical force in for the roller, normal to the flat surface there that the roller sits on. And then I've got a pin joint at A. Pin joints prevent motion left, right, and up, down. So I've got an REX and an REY. You okay with that? Okay.
You said A was a pin joint and C is a roller?
Correct, yeah. And those are kind of what you might call schematic symbols. For a pin joint, look for a little triangular thing. If someone's really, there might be a dot at the top to indicate the pin. The roller's the round thing. Okay? Those are typical schematic symbols to indicate those pin joints and rollers. Okay? Now our goal here is to find RA, X, REY, and RC. That's what we want to do. Okay, so we good? Now start with 3 possible equations, some of Fx, some of Fy, and some of moments. Okay? Now let's figure out, now what I want to do here, I want to solve this as easily as I can. I don't want to generate one equation with multiple unknowns. Okay, it's just a little trickier to do that. I don't want to do that. So what I would like to do here would be to start with one equation and one unknown. So what could you do on this? I mean, where might you, let's see, which equations might you use to accomplish that? Let's just.
Sum of Fx.
Yeah, sum of Fx will get that for you. That'd be one equation you could use. Are there any places you could take moments about that would get you one unknown?
Well, there's 4 forces that each act at different spots, so now.
Well, but some of those forces are known, though. Yeah, I think a moment about A might work. That might fit the bill there because, okay, and that's often a good idea on these is take a moment about a pin joint because remember on these 2D problems you can only have up to 3 unknowns. Pin joints have 2 unknowns, so if you take a moment about A, you'll only have 1 unknown left because 2 of them will run right through it. Okay. So that's often a good strategy on these problems. If you see a pin joint in 2D, take a moment about the pin joint. We good with that?
What if it were a cantilever?
Cantilever, we'll get to one of those next, but a cantilever, really, the solution process is pretty simple because you just go some of Fx, some of Fy, and some of moments about the support. and you're done. I mean, there's no strategy to how to solve a cantilever because all the reactions are in one spot. Everything's right at the wall. But with pin joints and such, you might have to use some strategy to figure out the best way to go at it.
Would you take a moment about that junction?
That's normally what I would do, yeah. You don't have to, but that's normally how I would approach it, yeah. Okay. All right, why don't you write up sum of fx equals 0 and solve for the REX? Let's do that. Getting 3464. Everybody getting that okay? Switch. Anybody have any trouble with that? Questions? Which way does that act? Yeah, it goes to the right, okay? Now there's two reasons for that. One is I'm pushing on it to the left, so it pushes back to the right. The other more formal reason is I assumed it to the right. I ran my equation, assuming it to the right. I got a positive answer, which verified my assumption. It does act to the right. Okay. All right, so that's taking care of RAX. It's 3464. All right. Now, still got two y unknowns. So sum of Fy is going to get me 2. I don't really want to go there, so I'm going to take moments about A next. So why don't you write up a sum of moment about A equation and set it equal to 0. And see what you get out of that. So what you're going to solve for is RC. So taking moments about a pin joint can be a pretty good idea because it eliminates two of the unknowns. See, RAX and RAY act right through the pin joint, right through RA. So they don't cause any moment about A. Okay, so I just go sum of MA equals 0, and then I put in everything. There should just be one unknown in there, RC, to be able to solve for it. Is it X the other way? That's 6,000 times 1.2. That would be negative.
Oh,
yeah, there we go. And the other one should be negative. Yeah. Now, watch your signs on these.
No.
$5,200, something like that. All right. So I'm taking moments about A. So being as I'm taking moments about A, I don't have to include any of the forces that act through A, because they zero out. They've got 0 moment arms. So I get 6,000 times 1.2, which is clockwise, so it gets a negative. Okay. And then I've got RC itself, which I want to solve for. That's got a moment arm of 3. That's counterclockwise, so it's positive. And then I just want the sine of 30 of the force on the end, because that's the Y force. The X force goes right through A, so don't worry about that. So sine of 30 times 4,000 times its moment arm, which is 3 plus 1.2, it's 4.2. It's clockwise negative. Okay. And then I just work through the algebra there, get the 3RC on one side and everything else on the other, and divide by 3, and I get 5,200. It's positive, so it does act up like I assumed. Doing all right on that? Got any questions? Doing okay? All right. So, so that gets you RC. And then, what else do we got here? We've got, we want to find RAY. All good. Okay, so we want to find RAY. What's the easiest way to get it? Yeah, just some forces in the Y. Don't mess with another moment equation. Moment equations are more complicated. You got moment arms and you got directions you got to be thinking about. So just take the simplest way to get something. That'd be sum of Fy to get RAY. Okay. I think it's 2,800 when you get it. I think anyway. Is it? Was it 2,800? Okay, good deal. Thanks. Just so FY. A little bit of trig on the one on the end, that's about it. Y'all okay with that? 2800? Okay. And like always, you know, take your time, set it up. Then when you get into more complicated problems, you want to be systematic, especially about how you do it. So don't shortcut. Take your time. Set it up the right way. Okay. Questions on that? Doing okay? Looks like we're doing all right. Now, if I want to check my work, I can take moments. To do it, I would take moments about a point other than A or C, because I want to check A and C. So I went ahead and did a moment about D on the very end, and ran the numbers, and I got 0 for my sum of moments, which is what I want to get. If you take moments about any place, you should get 0. Okay? That's what you should get when you take moments. And that's what that worked out to be, so that's all good. All right, so that's a good check. So keep in mind that a moment about any point should sum up to 0, because if it doesn't, that means that object will start to spin. Got any questions on that? Doing all right? Doing good? All right. All right, so that's one problem there. Let's look at a couple others here as we have time. Let's see, did it really? Oh, yeah, now what I did, now you don't need to take notes on this, but on this little example, I'm doing the same problem, but I just turned all the forces around. So I got REX to the left, I've got REY down, and I got RC down. It's the same problem, but I've made assumptions of direction that are the exact opposite of what I just made. And obviously you can tell this kind of crazy. The reactions wouldn't be pulling down if all the forces are going down. But I've just done that just to illustrate this deal with signs, okay? So if I do that, for sum of fx equals 0, I got a negative REX now because I've assumed it to the left. Then I've got minus cosine 4,000 because the 4,000 acts to the left. And the sum of those is 0. Now again, when I solve for REX, I get negative 3464. Now the negative on the answer does not mean it acts to the left. What the negative on the answer means is my assumption was wrong. I assumed it acted to the left. My assumption's wrong, so what that means is it acts to the right. I don't have to do any extra calculating or anything, I just turn it around is all I gotta do, okay? So the signs that go in indicate the direction you assume. The signs you get out tells you whether your assumption was right or not, okay? So that's the deal with that. So it's really not a big deal which way you assume these things act as long as they're on the proper line. It is a big deal if you don't assume the proper line, you know, up or down. You know, so like this one here, or RAX, I guess we're talking about that. That's either got to be left or right. If you assume for some crazy reason that RAX is going up like that, you'll get a bad answer, okay? So it has to be on the proper line, but it can be either direction on the line, okay? So just keep that in mind. And I've got other examples here too. Some of MA, I got RC down. So again, I get a negative answer. That means RC doesn't act down, it acts up, okay? That's the idea of the signs. Okay. All right, let's look at cantilevers. Now, cantilevers have a solid support at one end of the beam. So here's this street stoplight sign, or I don't know what you'd call it, stoplight support. They've bolted that thing over there on the post so solidly that that would be a cantilever support. They've bolted the bench right into the wall, so that's a cantilever. Here they've taken the beams from inside the building and just extended them outside of the building to create a roof. So you can, if you're just going to look at and analyzing this section of the beam, you can analyze it as a cantilever. Same thing there. Floor joists, they just extended them out to make a porch. That's a cantilever, okay? So cantilevers just aren't going anywhere, okay? They're totally locked in at the support. You know, in this case, you could just analyze that one section of beam as a cantilever from the post out, okay? So let's have a look here. Okay, we want a free body diagram of this thing. Okay, I'm on 405. Now that's a distributed load. The way you handle that is you find the area under the diagram, that's the load, and then you place that load at the centroid of the figure. Okay, so if you've got a rectangular figure, the centroid's in the middle. If you got a triangular figure, the centroid's at a third of the distance over from the right angle, which means it's 2/3 of the way over from the vertex. Okay, so that's where the centroids are at. So we've got a trapezoid there, and I don't know where the centroid of a trapezoid is. So what I got to do here is I got to break that up into a rectangle and a triangle. So because I know the centroids of those simple figures. And the truth of it is the formula for finding the centroid of a trapezoid is complicated enough where you might as well just break it into a rectangle and a triangle. It's easier. Okay. All right. So what's the height of the rectangle here and the height of the triangle? What are those heights?
So your rectangle would be 3,000 and the triangle would be 2,000.
Yeah. And I'm mentioning that because, you know, I've been teaching this for 20 some years and my battery's running low. That's no good. But, that's a mistake I see people make a lot. They'll just pull that 5,000 out because it's just sitting there, you know, it's written on the page. They'll say, oh, the triangle's 5,000 high, but it's not. It's 5,000 minus whatever the height of the rectangle is, which in this case is 3,000. So the triangle is 2,000 high. So why don't you find the force associated with the triangular load and the force associated with the rectangular load, and then put them at their centroids. Okay. So that'd be the first step in making this free body diagram, and then also see if you can get the reactions on that. So 2400 here, should that be? Let's do that. 1,000, oh, that is, yeah, it's 2,400. 7,200, 3,000 times 2.4. Yeah. Yeah. Doing okay with that? And then we want to place those at the proper location because that affects the moments, right? So the 7,200's on the rectangle, that goes in the middle, and the 2,400's on the right triangle. That's a third of the way from the right angle. But see, I know I'm going to take moments about the wall, so I'll dimension it from the wall. And that's 1.6 meters. And then what I want to put the reactions at the wall. I got an X reaction, a Y reaction, and a moment reaction. Okay. Now, I can look at that and see I'm not going to have an X reaction. It's going to zero out, but I'll put it on the diagram anyway. I mean, I write up the diagram first, then I run the equations to see, how things pan out, so to speak, all right? All right. Okay, so now I see that's the first step, and I break it down, and now I'm set up to do a moment equation about the wall, all right? So when I create these diagrams, I want to do all my thinking, geometric thinking in one step. I want to get everything just laid out on that thing. The next thing I'm going to do is just look at it and do a moment equation. I don't want to do both at once. And because, I kind of have a saying, I'm kind of stupid and I've accepted it and I've gotten over it, okay? And so what I do, I take all these steps to compensate for my lack of intelligence. And what I do, I try and do things in one step at a time and then have like functions that I'm doing in my brain at the same time. I don't try and scatter them all over the place because when I do that, I start making mistakes. And that's when bad things happen. So first thing I do, I get a nice diagram, all the forces, everything dimensioned. I know I'm going to take moments about the wall. I'm good to go. Now all I got to do is look at it and write up the equations. And like I say, if I start trying to do both at once, I'll make a mistake somewhere, okay? So we got sum of fx is 0, and that's rbx. That's pretty simple. Sum of fy is 0, that's rby minus the 2,400 minus the 7,200. So I can solve for rby. Then I can sum moments about b and set that equal to 0. 2,400 times 1.6 plus 7,200 times 1.2 minus, because it's clockwise, mrb. And I can solve for mrb. See, essentially, I've done all the thinking when I make the diagram. I'm not really thinking now. I'm just looking at arrows and summing things up. That's all I got to do. Once I make a good diagram, I'm good. We doing all right with that? We got any questions? I think you guys already handed in 241 and 2. That was Friday, I'm thinking. So what we got to do here, I'll add a couple, but we got those free body diagram problems. Now what you'll be doing on that, just do them right on the page, turn in the page. That's all you got to do. Don't write them up or do anything like that. Just do them right on the page. The page is 12A and 12B. and then do these other two as well. Their equilibrium problems, kind of get started on that stuff. And this will be due Wednesday. We'll go over it tomorrow. And that's November the 1st, I think.